The first step of any force problem is you need to decide what object you're looking at. This sounds simple, but it can actually be tricky, as many of the things we're interested in are a composite object. For example, suppose I have a box in the back of my truck. Depending on the problem, I might want the truck and the box to be my object, or I might think about them separately and just, for example, want the truck, or just want the box. How you decide what your object is depends on the problem. The next step is to identify all the forces acting on your object. You just want the force where your force is acting on your object. You don't want the forces where your object is the agent. Here's an example. Consider a table with a book on it. And I want to choose the book as my object. The only forces I would want to include are the force of gravity and the normal force from the table on the book. Okay. That's if I'm analyzing this book. I would not include the normal force from the book on the table. So the normal force from the book on the table is a force that appears in this picture, but is not a force that acts on this book. And so if we're analyzing this book, we don't want to include it. Problems involving force get quite tricky. The key to be able to properly model the situation is careful bookkeeping. The central bookkeeping tool is known as the free body diagram. A free body diagram represents the object of interest as a single dot. You then draw vectors for every force which is acting on the object. Only draw forces which act on the object, and the base of each vector should be on the dot. Let's do an example. Suppose I take a book and push it up against a wall like this. Let's draw a free body diagram. Well, we've already drawn our dot. Next, we have to draw all the forces. So let's identify all the forces. So first, I was pushing against the wall. So that is a force, which I can call force hand on book. I was pushing on the book, and the wall was pushing on the book. So it's another force, wall on book. That force of the wall on the book, that's actually a type of force we've seen before. That's a normal force. So we could also have written this as the normal force of the wall on the book. Okay, what else do we have? Well, we have gravity acting down. Okay. And then there must be forces acting up, because otherwise this thing would be accelerating down. And those forces are the friction forces, and there should be two of those. One is the friction force between my hand and the book, and the other is between the wall and the book. Force of friction, hand on book, and force of friction, wall on book. Okay. How did I know to draw those friction forces up? Well, I knew that if I didn't have any friction force, the book would fall downwards, and the friction forces oppose that motion. We'll learn more about friction later on. Now, the symbols I chose to use have the advantage of they tell me a lot of information and they are very clear. They say both what is the object that's being acted on and what is the object acting. So here, the force from the hand, from the wall, and gravity, that's from the earth, is what actually causes that force. Probably in most problems, you're going to want to use a somewhat abbreviated notation. So maybe you might do the same diagram, but instead of writing FH on book for the force from the hand on the book, I could just call that force just H. Right? Means the same thing. And instead of the normal force of the wall in the book, I could just call that force N. Right? There's only one normal force in this case. Instead of W sub B, I could just call this W. And these two friction forces, I could just call them, say, F sub H and F sub W for sort of the friction force from the hand and the friction force from the wall. Now, the textbook Knight, Jones, and Fields adds one more thing to the free body diagram, and that's a coordinate axis. I think this is a good idea, and there are two different ways to add the coordinate axes. The way the textbook does is you take your free body diagram and you draw axes coming from the dot. Okay? And that's a good way to do things. It can get a little messy, as in this example. Another equally good way to do things is instead of putting the axes right there, you put them off to the side. And I think that's just as clear, or maybe more clear even. I think either is fine, but having axes is a good idea. If you look at the other textbook we're using, the Nexus Physics, they tend not to draw the axes on their free body diagrams. The other thing that the book Knight, Jones, and Fields does is they add off to the side a vector representing the net force. And in this case, the net force is 0 because the book isn't accelerating. And so using the approach from that textbook, we would write over here, write F net equals 0. Okay. Or if I did the little experiment where I removed my hand from the book and we ended up with just a free body diagram that looks something like this, where you just have the weight and the force of friction, we can better guess that the F net is going to be downward. That thing's going to accelerate downward. Let's try the experiment. Look here. I let go. So in this course, when we ask for a free body diagram, we want a dot, a coordinate system, a series of labeled force vectors with their base on the dot, and then an arrow pointing at what the net force is. We'll do some more examples.